Screw it more to lab 4 than lab 3.
Well, lab 3 is easy.
Yeah, that's what I mean.
Okay, yeah.
Lab 4 is easy as lab 3.
Yeah.
Judging by how much code he gave us, it is. Or not. Although most of it's parameters.
With the actual code answer.
Can we start it for you?
Yeah, sorry, my machine is just really, really slow. Trust me, I wish I could wave a wand and make this thing quicker. I've been waiting this whole time I'm installing here.
Is the projector on?
I can turn it on, but the longer I wait to turn the projector comes on quick and shines my light and blinds me.
Oh, you know you love it.
Masochism.
The glow. But guaranteed we're ready, so it's good start. Yeah. Have the killer projector.
That's why I feel like I'm in a bad 1950s movie or something. Where were you on the night of the 14th?
We'll just go with the blind strip, so a nice projector can.
I know, yeah, and I'll have a horrible projector. I need to put on sunglasses though, so I get the stupid sunburn. Yeah. Put on like the spray fake tan, so it's like orangey. You know, looks like a 1960s Star Trek episode for aliens.
Sunglasses.
Sad true. Yeah. It's amazing how many aliens are suntan orange.
The planet's probably closest to the sun.
Yeah, it's got to be. The real reason the Romulans are invading, they want better suntan spray. We concentrated on weapons and we look horrible. Yeah, I hope so too, yeah. This make great on YouTube, stupid professor jokes.
Yeah, white light and flash. That's because of the shear joint. Okay, so Avi's lined up there, so I'll write stuff up on the board over here. Oh, he's not here. That's no fun.
Wait, hold on, I'm voting. Don't write yet.
I'll pull this down, and I probably will have to write a little bit off. Let's see. I got So this is actually the most complicated unit that's going on here. Save the best for last, because by this point you are all experts. Right?
At Thomasilla?
So you want a true challenge of your skills with Barrel. So what we'll do is we'll keep walking back and forth here just for obvious fun. Because statistically he is actually enjoying it. All right. This one, what we have to do is actually something at every stage. This is the one part of the system that pays attention to everything that's going on. Because as you think about it, it's the one that has to actually fetch the instruction. Up until now, you haven't worried about fetch, because you've picked up the things at issue. But think about what has to go on. I have to get that instruction first, so I'm going to have to actually fetch my instruction from memory. Now, usually we take these and decode can be thought of as part of the whole issuing process. So we can handle kind of decode and issue in one big area with an issue command. We've been calling it issue up to now. That's the usual case when you've got multiple different systems. We don't just call it decode.
because you also have to be able to see, can I send it to the different place? If you have a large pipeline system, you might even break it up where you decode and then you issue. Figure out what it is, send it out. As it goes on. Then I have to be tracking this. Right? So there's going to be a series of different updates that are going to have to come in. Right? In addition to filling up my queue, make sure I have commands, figuring out what's in my queue and sending them out. What else do I have to do? To track its status, don't I?
Right.
Okay, so there's going to be a whole series of different status updates that I have to handle too, isn't there? I've got to find out, is it now executing? Is it ready to write? All the rest of this kinds of stuff. So I have a bunch of tracking my status. So I'm just going to call it update status or just update. I have to handle all those status bits at the various update points that go on. Do I have to worry about the very end when write comes around?
No.
Yes. Because
No and yes. Who wants to defend?
I'll defend.
Okay.
So we have to worry about write at the end because if we're updating, if like our update's high, then we should write out, right? We should update the values in our reg file.
Okay. But am I the reg file?
Oh no, yours the queue.
The reg file
I'm the
handles
instruction
writing.
queue.
But
The
you,
reg file definitely has to worry about that.
Right.
Does my instruction queue have to worry about it?
no.
Right to the instruction.
Everybody says no? Then I'll say yes.
Okay.
Okay? And I will give you an argument to try to defend it. And then you can tell me whether or not you buy my argument.
Okay.
My argument is this. I do not want to keep that instruction in my queue for the rest of all time. I got to know when I can delete it. When it writes its answer, the instruction is done and can be removed from the queue.
Right, because we updated. So now we can move
Because I
on.
wrote. Do I care about write? Because update is all those little status bits in between. Do I care about write?
No, we only care when we're updated.
But you don't buy my argument.
I do one.
I mean, you make a decent argument, but I don't know if we want to do
So
that right.
how will you get it out of the queue if you don't check when the command finishes? You do have to remove it from the queue, right?
Right.
So how do you get it out if you don't use write?
Blindly.
Oh, I see. Yeah.
Throw a dart?
Monte Carlo.
Yes. Monte Carlo removal process. I mean, if you make it sound fancy enough, somebody will buy it. It's just- I mean, do I need write?
Yeah.
Yes, I need to know when you write. Okay, for our system, we're done as it's going out. There is another one for us. Once the write comes in, we'll update that status bit. We will actually add for ours one more step, which is a cleanup. One which will happen a cycle after. It will happen later to remove it out, a little bit after it followed out of queue. Now the reason why I do this is actually for a different reason. Okay, one, it makes it a little bit easier, but I could remove it from the queue right at the time when you write and I'm done. But there is an advantage to not doing this. And the advantage comes in if I ever deal with branch commands. We haven't built a branch command into this, but if I wanted to add a branch command into this, I need to be able to check if there's a control hazard. Okay? So I make sure that I appropriately handle things with it. Two ways I can do this. When I come to a branch command, I can just tell everybody no more issuing. Wait till the branch command completes and then you can handle it. Okay? This is the equivalent of slipping the system. Now, what's the disadvantage of doing that?
Performance.
Yeah, it's performance, right? Your system is just not going to perform as well. Now, obviously I'd like to be able to get something that's better than this, something that performs quickly. So what I would like to be able to do is to be able to keep issuing commands based on a branch predictor. But that means I could have tons and tons of commands that have been fetched and issued and have been sent out into our system in lots of different locations.
Right.
And those might finish faster than your branch command. So how do I undo them?
Send them to
If
zero.
it turns out I shouldn't have followed that.
You send them to
In
zero,
a
right?
pipeline, they can't finish before the branch command, so you're safe issuing them. But in a Tomasulo's machine, that branch command could be waiting on a load, and that load might page fault.
Right.
Okay? I could have millions of things that are ready to go before you. So I've got to be able to, in some sense, stop them. But what we do on this, if you ever do have a branch one, it won't be in these labs, but this is why I add this extra step in for a cleanup, is that we actually take them and we don't allow them, they write and they write to the queue. They don't write to everybody. And only the queue can send on the common data bus then. And the queue checks to see if all the branches before it have finished before it writes to the common data bus and cleans the instruction up. So it gives me one extra thing. It's often called complete, or completion. That it checks to see, is the command really complete? Has every contingency before it been checked? And if they haven't been checked, it will hold it. And it will hold it until the contingencies have been checked, and then we know were they good or not. And if it turns out that it shouldn't have issued the command, it just dumps it out of the queue and doesn't do an update to the common data bus. If it turns out it should have, it just starts writing them out as fast as it can. Make sense? So that becomes another reservations. Each line in the queue becomes a reservation station because it can hold values. Lots of fun stuff that goes on. In our case, we don't have to worry about it, but I'm just mentioning it because we have there. I leave the step in because it makes it a little easier on us and away we go. But that's why I have it there. So far, so good?
Mm-hmm.
So in order for this to make any sense at all, we have to have a picture in our head of what's going on. Okay, so I'll come way over here.
I got Zoom.
Again, and then we'll draw our picture. And it should be like about this big. Yes, Avi is thrilled. And provided a challenge for him. See if his lens is good enough. Good enough, Zoom? Okay, so on our instruction queue, remember we had 3 different sections. We had the instruction queue, and we also had 2 other sections down here. I'm not going to worry about the other 2 sections in here. This was your adder/reservation station, and this was our register file. It went on. You built this in Lab 2, you built this in Lab 3, we're now on the instruction. So this is kind of the smart one, so we'll call it IQ.
IQ.
Okay. What do we need to be able to track inside here?
Who's executing and who's done executing?
Okay, so we will need to know, whether it's execute, we need to know whether there was a write. Any other things we can think of we want?
What instructions are we waiting on? What's
Okay. We need to know, has it been fetched? And in our case, we're not going to decode, has it been issued? So we need to know, has it been fetched? Has it been issued? Right.
What's
Has
fetch?
it written, or you can call it completion. I'm not calling it complete because you can call it done too if you prefer. Done, complete, written, whatever makes you happy. Do I need to know anything else? Probably because I love you.
Who needs to get what? Like after something's done writing, where should it go?
Yeah, are there any reservations?
Do I need to know that?
We need to know what
Isn't
reservations.
that, the only other spots that have to update is here and here.
Right.
Shouldn't it know?
Well, doesn't it need to look at the reg file and then tell the next one that's kind of waiting to go?
Don't I just tell the reg file to do it?
Will the reg file tell whoever's waiting? No, whoever's waiting looks at the reg
Remember,
file.
we
I see.
wrote these things so that these ones are really responsive here. This is like our CEO. Right?
Right.
Does the CEO walk down to the, accounting department and walk through the files themselves?
No, that's right. The accounting department.
Way too slow.
Right.
You send for it.
Right.
Do
You've taken
this.
it. Right.
They do it, they give you the result. You're assuming they're not going to lie to you, but I mean, it's hardware, so you run it so it gives an error, and then clearly you made a big mistake. So we're going to assume that, they're going to do their, if they have to exchange, they'll exchange their things. But do I need to know who's working on it?
Yeah.
Yes, I do. Why do I need to know who is working on this? Well, because remember, execute and the write command that tells me it was completed when it writes its answer. Don't I get that information by it saying, by the way, reservation such and such is now executing, reservation such and such is now finished? Doesn't it? I mean, that's how it sends out the information, what's going on. So I can't update my fields if I don't know where it is. This is kind of like your project name. So I kind of got to know what that is. So when somebody says, reservation station 7 has just finished, the one tracking all this, right, my CEO here, I better know what that is. Make sense? Anything else I need?
Let's see. So RS tells you who's available and who's not available right now.
This is not a good thing to look at. If you're trying to look, this is stuff coming in and out.
Right.
If you're trying to figure out, what I've done on them, now you're looking at the internal variables, right? So remember where your data is going to get stored. Your internal variables that are inside of your module, your object or class, right? These are going to tell you what's being stored. The I/O tells you how do I know what to update, and what do I send out as commands. So right now we're taking a look at what's inside my particular module, so you should look at the data elements that are inside. When I start talking, how do I talk to the, adders, how do I talk to the reg file? That's your I/O. Okay? So the interface is between the units. Okay? Your internal variables is inside. So when we're walking through these, it's right here. Okay? Anybody see anything we are missing glaringly?
Current queue element?
We are missing, in some sense, a program counter that's going on, but right? Yeah. Program counter. What's a program counter used for?
Fetching?
We're going to use it
For
to
fetching. Okay. So that's telling me how do I load things into a queue.
Right, or PC relative?
Okay. Well, what's PC relative?
We add to the program counter and we go from the
And what do
program.
I use PC relative is an addressing mode.
Right.
Is it, as an addressing mode, is it something that's stored?
No.
No, it's a way in which you calculate an address.
Gotcha. Gotcha.
Just out of curiosity, what's PC relative used for?
Oh,
I know we use an LC3
For what?
Jump.
jump.
It's somewhat related to that.
Subroutines.
It's actually used for something different. You don't usually use PC relative, except for if you're doing like loops.
Right.
But that's not a data load.
Isn't it for...
Right? So, but when you're doing data, because it's an addressing mode, so I'm accessing data, I'm writing or storing. So PC relative is, you should know when there are addressing modes, you should know why the addressing modes exist. So if you look at them, you can tell what they're doing by what the address mode is. So PC relative, yeah, really, it's actually what they're there for, so you can tell. What do you think PC relative might be used for?
It's not for when you're...
Access close to where a program counter.
Close to where your program
Yeah.
counter is. Why would you want to access close to your program counter?
Because it's in cache.
Contiguous memory spaces.
But arrays are data, not program.
Yeah.
Right. Well, it's because
So
they
you
should
have
be...
to have data that's tapped in with a small section of code, because it's a little jump from there. When do you have a small section of code and data that gets stuck in with it?
A loop.
I don't know, because the loop, then you'd run out and you'd hit your data section.
Oh, gotcha.
So it would have to, if you have a data section, the program would have to stop before it ever reached that, guaranteed.
So
Subroutine.
that's what I kept saying. Subroutines. It's when you go on the stack.
This is how you make local variables to subroutines. We store them PC relative. So whenever you have a local variable that's going on, we store you have a program counter that's here's your code going on. There's a jump that comes down, you call the program, or you call this little subroutine, it goes down to the end and it will jump back. Right before and right after, that's the local vars. Add L. Local vars. And they're an offset from where the program counter is. And so this becomes where they're stored. And this is why you can't access them at other times, why they're protected. Because once you jump away from there, it's no longer that same offset. If I'm back here, it's not 10 lines up to get that variable, because you're not where that is anymore. So that creates a nice namespace protection. Right? Namespaces can be handled by pages, but you can also create local variables, right, where they are completely different. And the name of that local variable is the offset that goes in. It tells you how to get to it. So if you ever see PC relative, it's a local variable to a subroutine. That's what it's there for. Right? If you understand the addressing modes, you understand what's happening inside the program. Right? You don't understand them, it's all wild guesses. So, PC relative is not the one we're shooting for here. So think about this. I'm asking, what am I drawing up here? This is the queue, right? So my local variables, I should be looking for things that are part of the queue. So what's my status? How big is the status over there?
4 bits.
4 bits.
4 bits. Do you see anything up here that's 4 bits in size?
You can find any bits.
How big is fetch?
I don't know. Where is it?
What is fetch?
It's the current opcode, right?
Say it. If it's what it looked like you mouthed, then it's correct.
Current opcode?
It's fetch is, was it fetched or not?
1 bit. 0,
It's 1 bit.
Oh,
0, 1.
What's issued?
1 bit.
Was it issued or not?
Yeah.
How big is it?
1 bit.
1 bit. Execute is it executing now or not? How big is
1 bit.
that? Complete. Is it done or not? How many bits?
1 bit.
And what do these tell you?
They're just flags.
They tell you the
Status.
status of the command.
So the status of
Now I could have made 4 separate individual bits.
Oh, okay.
And you would have been able to access those very easily. And I thought about that.
No,
but
don't do
if I did that, you would never be able to handle anything that required write masks.
Right. We should be able to mask the stuff
So
out.
I ought to be able to make you mask things
yeah.
out in Verilog so you can deal with a compressed data array. So that's what I did. I gave you status bits, which are these 4 fields. And if you want to get the individual bit, you have to mask it out. Let me ask you a real quick question, and then I promise I'll answer it. How big is a Boolean?
1 bit.
Eh,
32 bits.
It's at least a byte. It could be up to 32 bits. It's usually 1 byte. It's the standard definition.
Why so? Oh,
Because you load things 1
1
byte
byte
at a time.
So you
So
can.
what that means is, when you go to try to save things by doing a little bool and you declare a bool, and you're thinking you're getting 1 bit of data, you only make 1 of those bits useful.
So how can we?
It's actually a 1 byte long integer that's either 0 or 1, unless you're on Microsoft. If you're on Microsoft, it's 0 or negative
0 or negative 1?
1. Which of these is a better convention? This should be honest. We're computer science people, right? Everybody hates Microsoft, right?
Yeah,
It
so
should
it's
be
0 or 1.
right?
Yeah.
Yeah, but unfortunately Microsoft is right. It should be 0 and negative.
Why'd they do negative 1?
It's all ones.
Oh, so it's all true.
So yes, so now you can actually do data correction with theirs. Since false is all zeros and trues are all 1, if you get 1 bit flip, you can easily tell it. You've got 8 redundant bits.
Ah.
Okay? So you can data correct the snot out of
That's
theirs.
32
You can't do
layers of
everybody else.
data.
Everybody else just wastes the bits. They at least do data correction.
They do.
Yeah.
They do.
So,
They do some.
It's exactly the same thing. It's zeros and ones. It's just all of them. When you put it through a logic command, it's going to exactly do your normal commands. It will just do them all in parallel. So you can validate the answer. The answer should be the same for everyone. So turns out that they actually have the correct way of doing it. Everybody else is wrong.
Go figure.
I know. You know. So next time you have a class with Quran, let me know. Have fun with that.
I know this is just a semantics question, but the fetch is the most significant bit of status, or is it least? I know, what did you have in mind when you designed it?
Yeah,
Your
so
designer.
that's pretty tough to remember, isn't it?
Yeah.
So what would be a smart way to do it to avoid having to know that? Because do you think a year or two later I remember? Hell no. I should make a parameter that has, you know, the busy mask wasn't fetched, issue mask wasn't issued, execute mask wasn't executed, write back mask.
Right, and then we can just mask it on
Then
status.
you can just use the name in the mask field and get the answer. But I mean, you get this code for free, so don't worry about it, right? So you will get the masks. So that would be my suggestion on is just anytime you have to access them, use the mask. The neat thing about this is if I wanted to all of a sudden say that I wanted to fetch it or that this has been fetched, I got several ways of doing it. I can or
The mask.
busy mask with it, or I can add the busy mask to it.
Right, 'cause it's 1 bit.
Either way, it does the same thing. Whichever makes you happy.
Adding is just storing, right?
In this particular case, the adding can have carry.
Right, and then
In
that
this case,
becomes
no
a.
carries can happen because no bits collide. So I've removed carries by the definition. Therefore, an add without carry.
Is an or.
Yeah. Okay. Good. So you can use those lovely little masks to do them. So all those things that we have right here, this is called status. Anything else that should be in the queue? I made a little argument for the reservation station that's holding my thing, right? Do I have a data element to do that?
Yeah, we do.
Reservation station that is holding my command.
Alright, holding.
Oh, what a good name. The reservation station that's holding is called RS holding.
There it is.
Amazingly 6 bits across. And notice both status and RS holding have whatever their width is if you need to hold them. And they have from the last queue element down to 0.
So what is that holding again?
RS holding, what's RS? The reservation station that's holding the command. Which one's working on it? Once
RS.
you issue it, you have to issue it to a reservation station.
Right.
I need to keep track of which reservation station it is because I have to see, is that reservation station executing? Has that reservation station written its result? That's how I can update the status flags. Make sense? Okay. Anything else that needs to go into the queue?
Next queue location.
I probably should have the instruction itself, shouldn't
Yeah.
I? I mean, up until now, do you know what I'm actually doing?
No.
No. So I probably need the instruction also. Now I know what my instruction is, I know who's working on it, and I've got its status. Do I have enough?
According to your First for loop, yeah, we got all three of them.
You look at my data declaration, you can see I have them all too.
I understand the for loop.
So you ought to be able to understand this too, right?
Yeah.
My queue has a last queue element down to 0. There's 3 of them that are in that. All right? So it's a queue that goes on to them. What else do I need with a queue though? Because it's an instruction queue.
Need a way to walk it.
Okay? So I need something that's going to point at where I am inside this. Do I need anything else for a queue? Think data structures.
Oh,
Right?
hold on. I
You
think
need an
there's.
iterator, right?
Yeah.
That's the thing walking through it. What else do I need to know?
You need a pointer too, right?
That is your iterator.
That's the iterator that walks through, right?
Yeah,
It's a pointer with an ability to.
Do we need the random access operators to be able to reference the data within the queue?
How big is your queue?
This one is 32. It's as big as the number of queue address bits, right?
So wherever I'm pointing to, I've got a couple things that are going on here. I need to track several things that's happening. This one's pointing to this particular queue, which is instruction memories. That's my program. This one queue, it has to point into here to say, where's the end of the queue? How big is it? How much of it have you used up?
Right.
Oh, right.
Because otherwise I'd have to be hunting through everything. So if you make a data structure, you grow it to a certain size, your memory is not naturally a queue. Your memory is naturally an array.
Right.
So then you have to have pointers that jump you around. Well, if I don't want to do pointers that jump you around, I can implement a queue on an array, can't I?
Yeah.
Of course I can. You just have to compress it and always keep rotating it so that the first element of the queue is always in your 0 spot. Right? If it ever builds up to the end, you've got to make sure you say, hey, I've reached the end of my queue, so I need to know how big the queue is.
Right.
And then you would either have to malloc, dynamically allocate memory, or you'd have to say, stop, you don't have enough memory, halt the whole program. Which one am I going to do here?
Halt the whole program?
Halt the whole program, exactly. Why?
Because we don't have enough memory.
Because you can't malloc hardware.
Yeah.
You know, if it wasn't there, it ain't there. There's nothing to malloc to. So
It just makes itself. Oh, that'd be great. Yeah.
That'd be I'll arrange for you to get a really nice degree. You can figure out how it can just synthesize itself as hardware or something. You've invented the board or something.
Self-replicating.
Right? So, you know, that's what this one is doing. This is telling me where the queue is that's going on. Now, do I have an iterator? PC is pointing into instruction memory. So it is an iterator. It's an iterator to instruction memory. Do I have an iterator for this?
Next queue location. Maybe? No, that's only
How big is that?
1 bit. I think it'll tell us much.
It's a 1 bit, so it's a flag of some type. That will probably make itself useful later on in workplace.
Yeah, I don't see an iterator for a queue.
Yeah. You know why?
We don't need one.
It's not there. You know why?
Because you wanted us to make
don't need
it.
it.
That's why, yeah.
Right? So what we're going to do inside of our queue, technically in a queue I can go anywhere I want, right?
Right.
I can access them all parallel if I really want, since it's on array. I can jump to them instantly, or I can walk through them in sequence. So what we're doing out of this, the whole reason we have a queue is as a priority queue. Who should be checked first as it's going on? So we will walk our hardware in that sense.
Right, first in, first out. FIFO.
But I don't actually need an iterator in the normal sense. I just need to set up priorities. The earlier you were in, the higher priority you have. So we did priorities before by making a memory location for it. We're going to do it a different way here, just so I show you different ways to do things. But if you want and you want to go that way, you are welcome to add in your own little priority bits.
So instruction memory is the entire queue. Instruction is where?
Instruction memory is actually, this is what we call a kludge.
A clue?
Yes, a kludge. Okay? It's a way of faking something. Okay? So we kludge something together. We take a bunch of junk and make it look like it's something more realistic. So this is actually, see, it's called instruction memory. Where is instruction memory technically?
In the last instruction element?
RAM. Right? Have you built a RAM module?
No.
No. Do you have time to build a RAM module?
No.
Right? You'd have to also build cache to interface with it and all kinds of other stuff. So this becomes kind of big and ugly as it goes. And I came to realize I was either going to get the internals of this or have you build RAM. Of the two, the internals of this is much more useful to you. If you're really interested in RAM, then take the computer engineering course or take 521 FPGA design. We cover designing and building RAM in that one. So, it's elegant once you see the difference. But it would be too much of a pain in here. So what I did is I just faked it. I just said, there's a whole bunch of memory, and I let you have a program counter in there. And you're not going to write a big program, so I don't need a big chunk of it.
Right.
Right? So you can think of it as prefetched, and this is a queue in cache, or either or whatever the hell you want. But really what it is I'm faking RAM, so we don't have to build it. So this is fake. Would it really be there? Okay. That's about the only thing I faked realistically in this whole system. The rest of it is pretty much how it would go, and then you'd have to add details. But the program counter would be there. I started at 0, the first instruction, and you walk through. Okay, so far so good? So we kind of have a thing of that other than this, which is actually going to be related to this area here, but I'll deal with it in a few seconds. Is this good so far? Okay. So what's going to happen is, when I fetch, what do I have to do?
Figure out what it is.
You got to use our PC to reference our instruction memory,
Right.
Okay. So before I can even use the PC to fetch something, what should I do?
Know where to fetch it
right?
from?
I check the status.
I should check to see, is there room here?
Yes.
Right? Because if you don't have room in here, why fetch?
Right, because the queue's full.
Because this is much smaller. And so I forget what I made this. I think it's like 7 or 8 elements in this. Right? So because this is fairly small, you have a decent chance that RAM could overflow this, because these commands are not necessarily fast. So before you do it, you should make sure there's room to stick it. How do I know if there's room?
You won't be in a queue.
I should check to see if it's been fetched already, right?
What do you mean?
If every one of these instructions has been fetched, they're all busy, aren't they?
Yeah.
So you can't use them. Does that make sense?
Okay, that's what you're saying.
Right? That's why we have that. That's why if you look up here in the name that I gave to fetch was busy mask. Is it busy?
Where's fetch?
Well, fetch is part of status. Has it been fetched? And I have busy mask, issue mask, execute mask right there.
Okay.
I literally just pick names to be a little bit.
I see.
Right? But has it busy? Has it been fetched? Right? Have you issued it? Is it executing? Am I ready to write back? Is it done? So it's called busy because I need to check to see, is it busy? So the first thing I have to do is walk through my queue elements and see whether or not they are busy. Okay? Do I look at every single queue element?
No.
Yeah, we mask them all.
No. We can just look at the end. Because if the end's busy, then that means everything before the end was also busy.
That's assuming it fills up in order. I mean,
And it should, because it's a priority
So
queue.
now we have to make a choice here. Are we going to force it to fill up in order?
If it's a priority queue, first in,
How
first
are we doing
out.
our priority? You haven't told us that.
Well, these are options we have, right?
Oh.
Because remember, I'm telling you, I'm not giving you an awful lot at this point. If you look at the amount of code I've put in here,
No, it doesn't go much further.
see, I set it up, and then I say, you gotta go do it. Okay? So all I do is initialize it for you.
What a guy. Next lab, he doesn't even do that much.
Other than that, there's nothing. So I haven't even told you what has to go in here in the steps. So that's why when I'm explaining this, you want to make sure you're following what's going on, because you have to figure out what goes in here. Right? Every one of these steps here, you're going to need a thread for
So we need 5 threads?
everything you do. Right? Anything you do, you better write a thread for, because they're separate. Fetching deals with one part of this. Issuing deals with another part. Updating deals with another part, right?
Right.
They're not dependent upon each other. They deal with different things. Fetch is only going to be changing what's in the instruction and what's the busy flag. That's all it's going to change. It doesn't need to deal with anything else. Other than you could say, okay, maybe I clear stuff if you want. If you haven't already cleared it, I'd suggest you clear it when you clean up. But, whatever. You can do it earlier if you feel like. Huh?
So what's fetch need to check? I'm sorry.
Fetch has to pull the instruction in, doesn't it?
Yeah.
Does fetch know who's going to be working on it?
No.
No, issue's the one who has to deal with that. Because it goes out to issue and it finds out who's working on it. Right? Fetch means I find the command. I've discovered the instruction, and I should mark that I've done that, shouldn't I?
Right.
Right? Once I've done that, then I need to be able to say, hey, can you do this for me? Right? At that point, I know the person working on it is Kenny.
Right.
Right? So it's not until I issue that I know who's working on it. So issue works on this and it reads this.
Right, so it gives my reservation station the option.
And then it will have to update this field. Hasn't been issued.
Okay.
Make sense? How about the execute? What does it need to look at?
Is it being worked on? Is
It
it?
needs to see, well, yeah, you need to check, whether or not these have happened here. But it needs to know who is doing the work, and then it will update, is it executing?
Right.
Because it'll get a signal from the outside thing saying, hey, by the way,
I'm running
reservation such and such, I'm now being worked on. And then it has to update its field. So it looks at this and updates this. So there's nice separations. They don't all write to the same areas, do they?
No.
They write to independent parts.
Right. It's pretty compartmentalized.
There you go. So that's why it's safe. Make sense?
Mm-hmm. It's getting clearer now.
Okay.
So,
So think about what you have to do just for fetch, because that's what we're going to deal just with today. We will fetch. Okay?
okay.
Keep it nice and small. You have to check to see, has it already been fetched? If it has been fetched, you don't want to fetch it again. But where will I need to be? Should I normalize my queue?
We normalize the queue.
Should I compress my queue so it's all nicely set up? What's the trade-offs?
If we compress it, then we're bound by how many things we can get at a time.
Well, you can't throw anything, can you?
No.
I mean, if I've got 4 elements in here,
Right?
I got my 1, 2, 3, 4. Right, there's my 4 elements. Right? 1, 2, 3, 4. Now, I load the first instruction in. Next cycle, I load the next instruction and I try to issue the first one. Next cycle, I'm checking on this one, or I'm loading this one, and I'm trying to issue this one, and hopefully I'm executing on that, so on and so forth. If I follow through that, eventually this one will get fetched, and then this one will complete. Do I want to have the queue wrap around so that, this one is now the new command?
Kind of like a circular queue?
That's a queue, so I can make the queue wrap around as it goes, right? If I do that, I have to have a pointer to where is the beginning of the queue and where is the end of the queue. Did everybody build these inside arrays?
Yeah.
Built a queue inside an array
Yeah.
as you're wrapping around, right? If you let it wrap, so you don't have to keep compressing your memory as it's going on, which is slow, then you have to know where is the beginning, where is the end. Right? If I bother to do the thing that once I delete this, I shuffle everything up, then implicitly I know where the beginning is. It's right there.
Right.
It's always in the same spot every single time, and I don't need a beginning flag. When I delete that one, I just move the whole thing down. That make sense? Then I have to move the whole queue very quickly. How long does it take to move a queue in software?
And
And how long does it take to move in hardware?
1.
1. Why?
Because
Shift register, I just have
yeah.
wires connected between them. I just go, everybody shift. I just walk. So what's a pain in the butt to software is really easy for me. So how tough is it for me to do a shuffle?
Not tough at all.
Hardware-wise, it's not that tough. You guys writing it? I don't know. We'll find out, right? But it's doable in hardware. So I can move the whole thing, big O of 1.
So all that would be part of the cleanup.
Exactly. Cleanup has to shuffle the queue. You are exactly correct. Cleanup is the dangerous stage.
If you don't implement it correctly.
Well, because if other people are writing while you're shuffling, you're in
Yeah.
trouble.
So would it be safe to do cleanup on the negative edge and just do everything else on the positive edge?
Ah, you are correct. You must separate between them,
Right.
with cleanup being on a different edge of the clock than every other operation. But you need to decide, given on how other things are sending and when their data is valid, you need to figure out, should it be positive or negative edge.
Okay.
Okay?
And all of these are on the
If it has
same.
been set up correctly up until now, there will be a correct choice. Right? All the signals coming to you will be valid at a particular edge of the clock. It is your job to figure it out.
Oh, okay.
Okay?
So
So cleanup would be on the one
Whatever
where
our
things can change and when you don't want to check. But we don't have to do cleanup right now. But realize, so compressing the queue, keeping it nice and stacked so it doesn't rotate around like that, it's reasonable to do. Right? So the end of the queue, everything that's inside the queue before that end of queue element, should it be already fetched?
like prefetched?
Because by the time
Should
you
it
get
be
to cleanup,
fetched?
all your fetches are already
Yeah,
done.
the only unfetched thing should be wherever after that.
Right.
You fetch something, you have to move the queue pointer down and mark it.
Right.
Right? Make sense?
So in the beginning, the end.
So you should be able to just check one place
Yeah, the end.
to see if I can fetch. You need to see whether or not that thing is pointing at the end of the queue or not.
Okay.
What is that called again? Do we have a pointer? Yes, I'm ready.
So.
It's called like queue end or
Oh,
something.
I see.
End of queue, right?
Last queue element.
Could be. Queue end,
Q end. Where's Q end?
right? Queue end points to the end of the queue.
Oh, there it is. Clear. Where's clear? Clear is 0. Okay, so that's what I thought. So in the beginning, it's at the end, right? The end and the beginning point to the same place.
This is pointing at.
So we need to check if we're at the end of the queue. If we're not, go ahead and fetch everything because we need to fetch it. And then we should also increment the queue end
So
if we do.
If you do fetch, you should point it to the next element, otherwise it's not pointing at the end of the queue anymore.
Okay.
Okay. There's something a little tricky about this queue end.
yeah,
Yeah, it's backwards. Because when you're at queue end, you're actually at. the
but see,
last
that's
value.
that's what I was saying.
Zero.
So at the beginning, the end and the beginning point at the same place, right? So we
So
can.
the beginning of the queue is automatically always the same spot, right? I cleared it, which means I set it to 0.
Right. So.
Right? Which means at the very start, I said, there's nothing in the queue, and I've pointed it at 0. This is location 0, 1, 2, 3.
Right.
Right, in this particular case. And I've pointed it at 0, which means this is where you want to update to.
Okay.
It points at the last queue element.
Right.
How many bits to address this queue?
1 bit. No, no, no.
Minus 1.
Yeah.
There's how many elements?
4.
4.
2.
Or
2
each
bits.
4 bits, all 3.
Why do I need 4 bits?
Oh,
We've got
2
4
bits. My
elements.
bad. Sorry.
In this particular case, I need 2 bits, right? Especially 0, 1, 2, or 3. So
Right.
there's 1, 1. Okay. So that's what I've done here, right? 0 up to the number -1.
I see. Okay.
Right, so that's bit 0, bit 1. In this case, it'd be 0 and 1. Okay. That makes perfect sense, doesn't it?
Yeah.
What do we do if
There's
we're
a
all full?
challenge to this, though.
What do we do if we're all full?
Ah, that's the challenge. Very good. So you saw the problem that comes in. Once I do this, at 0, that means this is where the next empty element is.
Right.
Right? When you increment it, right, this is now filled, this one's empty. Once you increment it, right, you load something in, this is now empty. Right? You get the next one. This is now empty. What happens when I do get the next one? I'd like to be able to fill this, right?
You need one extra bit.
Ah. I need a bit beyond what I need to address. I need something to be able to tell that, you know, my queue is legitimately full or not. Okay?
So that should actually be not -1. That should be Q address bit.
So there's two ways you could do this, right? You could actually set an extra bit that's in here. That's one. Okay? You could only allow you to take 2 to the n -1
Elements.
instead of 2 to the n elements.
Right.
So the last entry
Is the
is
last.
just,
Yeah. It's just.
you know, it's literally the address. If it gets to 3, there's no 3. You just know that's a no-go. That's good. Or I have to have some type of flag that says that the next Q element is legitimate or not.
Okay. Well, we have to.
Right? Because I can have an actual address thing, and I can have something that says next Q element is good, next Q element bad. But I have 0 through 7, right?
Right. Well, we have 3 reservation stations, so let's
Now,
just do 3.
if somebody really says, hey, look, I'd rather do one of the other addressing things, I'm okay with it. If you want to go one of the other ways, you're welcome to. I put one method up here. I also can have a flag that tells me whether or not this is pointing to legitimate address space or not. The next Q location is good or bad. Right? It's in the legitimate address space or not. And I could just tell, you could have recalled, you could have called that Q full, right? As it goes on. So I could have a flag that says full or not full, and then I just use the addressing bits. I could just stick that flag, I could stick it into the queue itself. And then if it goes above a certain space, it's automatically been flagged out and it's done. Or I could reduce the actual size of the queue so it's not a power of 2, it's a power of 2 minus 1. In which case the last element means full. Those are 3 different conventions. I don't care which one you really want to do. Okay? I've set it up for the first one I described. A flag to tell you, are you in the space, and then something that's pointing to the addresses. But if you would like to do it a different way, I'll perfectly accept it. Okay? You are welcome to so do. But you should tell me. Because I don't want to be hunting through your code to figure out which one you did.
That's what the interface is for, right? All right.
Right? So you tell me this, you know, you can say design method, hey look, I'm, you know, in your method area, the interface is going in and out.
All right.
The method that's going in here, you can say, hey look, you know, when I'm dealing with this is why I'm doing it. So, does it make sense?
Yeah.
Can you repeat it one more time? Sorry.
Okay, so you could either have 3 elements in the array,
Yeah.
right? Or in our case, we could have 7 elements, 0 through 6.
And that's the
Okay.
you set it up for it now?
No, that is not the way I said it. All right, but that is one way you could do it. You get one less element in your queue, but it ain't the brand new thing. I don't know what else you call it. It's 7 versus 8 elements in the queue. It won't be a big deal. Okay? You could leave all the elements that are in here, but instead of having 2 bits to address it, you could do 3 bits to address it. And if it's ever greater than 3, then you just go, it's pointing past the end of the queue, no good, dump it. Okay? That's much like the drop one element thing, except you're wasting your address space a little bit. Okay? Or you could have a pointer into the queue, treat it just normally, and then have a flag that says, is the address good or not? right? Have you reached the end of the, is the next queue location good or bad? You can say, if you want, you can rename this and say, is it the end of the queue? Right? Have I reached the end of the queue? I didn't call it that because I already had queue end and I didn't want two things called, queue end. But, you could call the flag whatever makes sense. Change the name. Does that make sense? So you got 3 options. Pick one. Everyone makes sense. You just know there's options.
Now the flag will get set in, right?
Well, if you move the flag, right, that pointer and the flag itself get handled, when you fetch it, you shift things down, right, because you're adding elements. When you go to cleanup, the last stage, you delete things out of the queue. It's going to shift the other direction. So the end of the queue increases in fetch and decreases in cleanup. Does that make sense? All we're dealing with right now is fetch. Okay? Just worry about fetch.
So then I'll just get if next queue location done.
Okay.
Okay.
So you need to check, right, before you actually go fetch something, you need to see if the queue has space. How you will check that will depend on how you set up your queue format. Right? If you're doing it the way I have here, I just check one bit. Is the next location good or bad? Okay? If you expand the bit, you remove this -1, delete that, then you would just check to see whether or not the value of this QN is bigger than the total number of the last Q element. If it's bigger than the last Q element, then you're done. Okay? If you go to the thing where it's a reduced space, all you have to do is redefine your last Q element to be 6 instead of 7. Now your Q is smaller by 1, in which case, and then you delete this, and then you do that same check the size thing. Is the QN bigger than the last Q element? If it is, don't fetch. Does that make sense?
Right.
Okay. So whichever way you go, pick one, do it. So you check, is there space in the queue? Let's assume there's space in the queue. What do?
Fill it up.
We need to
Fill it
grab.
with what?
The instruction.
How do I-
You
So we
fetch
look
it.
into instruction memory at PC and get
And
that, copy that into.
Into instruction.
Instruction.
Yeah.
Right? You take from where the programmer counter is pointing into instruction memory, and you copy it into the instruction field of the available space.
So we should do a for loop.
Why should you do a for loop? How many you
Oh, that's right, because we're already there.
You fetch it.
Well, we should do a
I'm fetching one at a time. Okay?
Right. So we should do a for loop for that one iteration. I equals 1. I is less than 2.
Awesome, yes. So,
Loop away.
It's called watermarking, guys.
Roll that.
that's a fortitude. Okay. So, yeah, you pull that particular instruction over, right? So I pull the instruction out of instruction memory. The program counter is pointing at it. What do I need to do after that?
Assign it to instruction QN.
Huh? Well, if I've pulled over and I've loaded the instruction from instruction memory. Are my pointers pointing in the right spot?
No, we need.
No.
My status field's correct.
No.
So what do I have to change?
You have to update them.
I have to update the program counter.
All right.
What else do I have to update?
Our pointer to our queue.
You have to handle the queue end and potentially the flag, because you could have just pushed past the end. Anything else I need to update?
So QN plus plus, then we just add one element to
Except there's no plus plus.
QN equals QN
But
plus
yes,
1.
that is the correct idea, right? QN, plus
like
plus,
give
and
it
then you
away
see if
to
the
it.
result is smaller than what it really was to begin with, or whatever you want to. And if it wraps around, that meant you went
Oh, then
outside
we
the
need
green
to
space.
pull
Then you'd have to set the flag. Okay. So, but there's a lot, you can handle that whatever way makes you happy.
So we upgrade the program counter and then what do we do?
You update the program counter, do you have to update the queue in?
Yes.
Yes.
Yeah, of course, right? You just load something into the queue, so it just moved. Anything else needs to be updated?
We need
Potentially, the flag could be changed, so you have to handle that. That's kind of wrapped into that. Anything else?
we need to update any of our status bits.
Do you have to update a status bit?
No.
Ask just to fetch it.
It's a good question to ask, too.
I don't know if we do it now or we do it on issue.
No, we do it every time.
Is it busy now?
It is. So update it.
Was it busy before?
No, it wasn't. Well, it shouldn't have been, because if it was, then we
Okay.
should have been fetching.
So therefore, I
Update
should
it.
probably update at least one. Probably the busy flag, right? So was it fetched? Because I just fetched it, I should update its fetch. Right? Is it busy now? Have I done everything I need to describe how I get an instruction from instruction memory into the queue?
Yeah. No.
You know, your only other option is else the queue is full. What do you do if the queue is full?
Error.
I don't do anything.
Oh.
It's not even an error, it's just wait.
Just waiting
So just, if there's no space, wait till next cycle, maybe there will be space. Because somebody else is gonna come in and occasionally remove stuff. So we just go, no room, I can keep playing, you know? So it just sort of keeps there, you know, doing nothing until all of a sudden it notices there's space to move something, it goes, oh, space, boom, next one in, so it's playing. Right? So all it's doing.
So it's just an empty else. We don't have to put a delay here, right?
Isn't that awesome?
Because the ALU already has that delay that you put in.
So all that's saying, so in our case, we're just gonna say, hey, we're gonna finish it in no time. So the flag is busy, take care of it. We have to move the pointers, we have to copy things across the instruction.
So we're gonna.
Make sense?
So we're gonna order that mask against status. but
That's
which-
one way you could do it,
Which
yeah.
status position though?
As instruction memory.
Well, no, it's with the Q element.
Where should I do it?
Oh yeah, status of the queue.
Least significant bit. Your element. Because
We should.
Yeah, but do I need to know where it is?
No, we just mask it. We just or it
Just
on
use
there.
busy mask.
Yeah, just or the busy mask onto
Busy
that.
mask does tell, I mean, it is the least significant bit.
Right,
If
but-
you consider the right side least significant.
But
bit.
which status element do we do that to? Do we have an array of status?
You do have an array of them.
But-
Which one should you do it to?
The first one,
Same
Should I do it to the one I just fetched or to some other random one?
To the one you.
probably the one you just
Yeah,
fetched.
then you just know where it is, don't you?
Yeah. It's a PC, right?
Oh no.
I mean,
That'd be QN.
if you're able to copy over the instruction into the instruction area, you have to know which one you're doing it to, right? So if I'm pointing, I'm saying this is the end of the queue right here, and I'm copying in an add command, I would copy over, you know, whatever. Add R3, R2, R1, say that was the command I copied in. And then I would now say, it's been fetched. And then I would move this particular counter, it's got to point past the end, which in this particular case, I can do in a variety of different ways. I could use and set the
I really have
flag
to look
to
at.
say that I'm past the end, you know, which whatever you want to call it, you can call it true, or I can make a constant that's past the end, or what else. As I want, I can do parameters and that kind of all this stuff. And I have the particular queue end itself that's going on. Great, I can do it that way, right? I could do it by, I had less space. There's lots of ways I can handle it. I also have this lovely little instruction memory out here. And the program counter is pointing to that command. And I better have it now point to the next command. So next time I come around, I grab the next instruction. If I don't increment the program counter, what happens?
You just keep fetching.
You keep
the
fetching the same
Keep
thing.
fetching the same instruction. All right?
So
Pretty
then-
boring thing.
So then,
Yeah.
our program counter and QN kind of be incrementing the same? Because we're going to increment program counter and then QN.
They're going to increment, but notice you should, you know, your program could be really long. Your queue will run and have to stop and hold. and then you'll keep running down to the program.
But I mean, for the initial fetches, that's kind of.
For the first ones, it'll start, just pulling them right in sequence.
Okay.
Then it'll fill and the process will stop. Then the queue will empty up a little bit and it'll refill.
Right.
But this one will keep increasing because we have no branches.
Right.
Whereas the queue will empty, refill, empty, refill, empty, refill.
Okay.
That make sense?
So do we handle updating the program counter in fetch? Yeah.
Is it something you did in fetch? Are you the one who knows that it happened?
Yeah.
Would anybody else know that it happened?
No.
Then you better do it.
So,
Right? If you know and nobody else knows, then you're the one to handle it.
But in
Right.
fetch, you're only going to fetch if your instruction spec isn't full, so your program counter won't get. Oh, okay. Never mind. Answer.
If there's no room, do nothing.
Yeah.
Oh, yeah, so
If there's room, hold the instruction over, update the status bit, move both of the cue pointers.
Okay.
and
Right?
Yeah.
That makes sense.
yeah.
Fetch is the easiest one of these. Well, because it's completely internal. It doesn't rely on any outside information. Notice I haven't talked about the interface yet.
Not a little bit.
You know why?
Because it doesn't matter.
Because it's irrelevant. What's outside there doesn't matter. I'm only dealing with here. I'm not talking to them. Fetch does not need to know about the rest of the computer. Fetch only needs to know where the memory is and where the queue is, and it just updates it. Okay? Somebody else is going to have to worry about the rest of this.
I thought I was missing some I/O.
What's that?
I thought I was missing some I/O. I guess because I'm used to instruction memory being different than instruction
Notice
queue.
none of these other stages knew when fetch was happening. Okay? Because realize I might fetch an instruction and those reservation stations might be full. So I might fetch an instruction and then 50 cycles later be able to issue the dumb thing. So there's no direct correlation time-wise between them other than you have to fetch it before you can issue it.
Do we have to do a small check on the PC to see if it's at the last element of instruction?
Yes. Now,
But you made
in a
it-
big computer where this is going on, it would be to check to see if there's a page fault. And you wouldn't do it. That would actually be handled by the page fault, the virtual memory thing. If you go off page, it's not in memory. It would throw a page fault. The OS would then, right, your program would get stopped automatically. The OS would come in and say, oh, what do I need to do? Oh, I got to load a page for them. It would load the page, it would reset memory so it looked correct, and then it would restart your check.
In our case, our fetch just
So
shut
in
down.
your case, you should just check, right? Once you reach the end of it, we'll call it done. But I'll tell you this, in this particular case, your last queue element is 1023. So I gave you 1K of memory.
Yeah.
You're going to write a simple little thing to calculate a few pentagonal numbers. Do you think it's going to take you 1,000 commands? Do you think it'll be anywhere near 1,000 commands?
Hopefully not.
Hell no.
Oh my gosh.
So, I mean, I would just check it just so you have a reasonable way to stop. But,
So when we get to that point, are we going to create our own instruction memory at that point with all the instructions we want?
Yeah, and then we read in from it. Like
it's
this.
already there.
Yeah.
You just write them in. We declared instruction memory.
Yeah, right now it's just a for loop of just junk, it looks like.
Yeah, at the moment, right, when I'm going through and initialize, remember, so I have an I, which is an integer, right? I say I'm not issuing at this moment, right? And I walk through all of my queue elements, I clear them out inside, that's the regular queue itself. And then inside instruction memory, what I do is I say, to the adder, do an add. From, okay, then I have, register 1 plus register 2 goes to register 3. The rest of the bits are clear because it's irrelevant. Okay?
Should be doing that.
So, and all I did is so that you could actually go through and you can make your own commands later on. Because remember these, I said this is where it's going to. You only have an adder, so you will always be making adder. You would just say, is it an AOU add, an AOU subtract, is it an and, is it an or? Remember we had all those
Yeah, we'll just
little commands?
throw our commands though in there. That's cool.
Yeah, you just throw your commands right in, and they're all defined right here. You add, subtract, or, and, not, XOR. Those are the commands you have available to you.
We put an issue in.
Well, I'm just saying, he was asking how you declare instruction memory.
Oh, okay.
When you go to write your program, instead of just going in and writing, I wrote, 32 commands that are just kind of generic, which is just register 1 plus register 2 goes to register 3. And I copied it 32 times.
Okay.
Right? When you write your program, you'll have different commands.
Right.
You'll just put them in sequence in here. Write to instruction memory 0, your first command. Instruction memory 1 gets second command. So on and so forth. Yeah. It won't be a lot of commands. But you actually get down and it'll always be adder, and you have add, and then you've got your 3 different registers going, and it's always 0 at the end. So you can just take that one line and copy it and then just manually increment I. Yeah. But in this case, I'm not having you do a real program for the first one, because you're not connecting everything up. You just need to see, is it there, and can you do something? So this was just quick and easy.
And then lab 5 is where we hook everything together. And then lab 6 is where we actually
Where
use
you write the cooler version.
Oh.
So in lab 5, you can put whatever the heck you want in there, just to see that it works.
You didn't even give us a timing diagram for lab 6, did you?
For lab 6, can you imagine how big that timing diagram would be if I dumped it in there?
Yeah.
Right?
Be awesome.
Be huge. Right? In that case, for lab 6, how do I know if you're right?
We'll
We.
get the right output.
Yeah.
Look at your
It's
output.
black box testing.
Yeah. Right? Because I'm just integration testing. And integration testing is easiest done in black box.
Do you want us to draw pentagrams too with our Verilog
that's the
code?
case.
I'm just kidding. That'd be so cool.
You go ahead. So,
We can. I can throw it to an FPGA and start crossing.
okay. Does the first part, how to do fetch, make sense?
I
Yeah.
think we know all the
The
person
concept.
pieces we
Yeah.
need.
We can code that
So,
up.
best thing I can say at this point is try to write it.
All right.
Okay? Try to have it done by next time.
Okay.
Okay? That way you can either hit me with a question,
Or we can
or we
move
can
on.
move on and talk about some of the other steps that have to go on.
So there's only like 4 things then. Check to see if we're full, grab the instruction, increment program counter, set our status flags,
Right.
increment our
Increment our QN, and then, but then we should also check
And
C.
you have to know when to do it.
Yeah.
Positive edge or negative edge of clock.
Right, yeah, that'll be when the thread. Start with all.
And that should be synchronous with the other modules, right?
You should watch to make sure, because you're not going to, all these things are doing, this, and this are all updating and writing to different areas of the queue, right?
Right.
This one's writing to instruction, fetch, and moving the pointer. Issue is writing to RS and issue. Execute is writing to execute. Whatever I called the last one, write. Write is updating complete. So far, nobody has had to write to the same field, have they?
Right.
We agree? So they're completely independent. So all of those can happen
At the same time.
same clock pulse.
Right.
Right? There's no chance for them to ever write to the same spot and get somebody writing a 0 and somebody writing a 1. At cleanup, I'm going to delete a command, I'm going to shuffle everybody.
Right.
Where do I have to write to?
The queue.
Everywhere.
Everyone. Yeah, everything in the
So
queue.
cleanup writes to everywhere. So it conflicts with everybody, doesn't it?
Yeah.
So these ones here can be at one edge. This has to be at the other edge. Otherwise, you've got a problem. So you have to separate them. Okay? That's the other reason why I separated them up like this. Because otherwise, I run into a big problem trying to update my fields.
So we should be done with this Tomosula machine before the quarter is over, right?
Oh, hell yeah. We
Okay.
should have the Tomosula machine running in about two and a half weeks.
Okay, that's what I thought. The quarter ends in like 6 weeks, right?
So you should have enough time that we can do first an integration testing, and then you ought to be able to write a program on this thing.
Right. And then whatever time's left over is gonna spend making
You should
sure.
write a program that's going to calculate these